So I have a typo to correct from last time. And so our usual setup is with a random variable x. It's a map from omega to I. And in particular, if we have an outcome little omega, it gets mapped to x of omega, which is some little I living in the index set. And so over this space omega, we have different sigma algebras, maybe F, maybe script B. And last time, there was an example that we did, the last example that we did. We had this BF, the finest sigma algebra. And it is supposed to be 2 to the omega, so the set of all possible subsets of omega. And then we talked about how there's a partition corresponding to this. So I'm going to write it as this squiggle arrow. That there's a partition over I associated to this. And we wrote it as capital pi. It was the set of singletons. I in I. And there's a notion connected to this, a definition. And we're going to generalize what we saw with this. Remember this example, we ended up with the expectation. The conditional expectation was actually equal to the random variable itself. In other words, this sigma algebra contains all the information that we need to know about x. And we can actually generalize this. We'll need a definition that x, the random variable, is measurable, which means that for all I in I, the inverse set, x inverse of I, this is, x may not be a one-to-one map. It can collapse things. So this inverse set is possibly a set, not just a single point. It's the set of omegas that get mapped to I. And this x is measurable, with respect to something, with respect to, let's say, B, the sigma algebra, if and only if x inverse of I is, as a set, an element of the sigma algebra B. So that's a definition that we'll use in a moment. So now this fact, generalizing what we saw in the second example last time, is that, in our example, our random variable is measurable with respect to BF. In fact, any random variable is measurable with respect to the finest partition. Let's make this a two-part fact. Any random variable x is measurable with respect to this BF. And one way you can see this, if you think about the inverse set, x inverse of I, this is a set. And any set is an element of 2 to the omega. So this fact is pretty easy to see. And then more interestingly, the second fact is that if x is measurable, now I'm really abbreviating measurable, with respect to some b, some sigma algebra that we have over omega, then we see happening what we saw in the second example last time, that the conditional expectation of x given b is exactly x. So we saw this as an example, and now this is a more general fact. If you have any random variable that's measurable with respect to b, then the conditional expectation is x. In other words, b contains all the information we need to know about x. Expectation? No. That was the example number 1 from last time was the expectation of x. So expectation of x is a very rough measure of what the value of x is, right? It's just the mean, the middle of the distribution. So the expectation of x doesn't tell you a whole lot about the random variable, the whole random variable. It's very limited information. That was example 1 from last time. Now here, x is itself. It's the whole random variable. It's all the information about the distribution. And so this conditional expectation, this is better than E of x. That's what I'm trying to say. This has more information. Okay, so that is a generalization of the example we did last time. And now I want to tell you about the law of total expectation. So we did the law of total probability recently. The law of total expectation has a similar flavor. With our setup, our random variable, x from omega to I, and b is a sigma algebra on omega. Then, this is also called the law of iterated expectation, that if we take the expectation of the expectation, conditional expectation of x with respect to b, now in general, this conditional expectation is a random variable. We talked about this. So it has a mean value, an expected value. So we take the expectation of a random variable, we get a number. So this whole left-hand side is a number. And then the law of total expectation tells us this is actually equal to the expected value of x. So, in fact, a special case of this law of total expectation we can see from this line. If we take expectation of both sides, we get exactly this equality. But this holds in general. So this line holds when x is measurable with respect to b. But even if x is not measurable with respect to b, we can still take this double expectation and get the expectation of x. So this is a very useful fact that has applications throughout probability and statistics. One cool application I just want to mention is the Rao-Blackwell theorem. This is a theorem in statistics about estimators and how they get improved. And one reason I wanted to mention Blackwell is because he was a PhD student here, a student of Doob. And there's a famous quote of Blackwell. So he got his PhD here, then he went to do a postdoc at the IAS, the Institute for Advanced Studies. And Princeton wouldn't let him take classes or work at Princeton. And so he went to be a professor at Howard University. And then he went on to become the first African American to be a tenured professor at Berkeley. And Berkeley is where I got my PhD. So here's the quotation of Blackwell. He says, basically, I'm not interested in doing research, and I never have been. I'm interested in understanding, which is quite a different thing. And often to understand something, you have to work it out yourself, because no one has ever done it before. So, words to live by. So the law of total expectation is that if you take the expected value of the conditional expectation of x with respect to b, you get just the expectation of x. And so now I've been emphasizing this idea that sigma algebras contain partial information about random variables. And now we're going to talk about a sequence of sigma algebras and how they give us increasing information with each. We can think of it as a step in time. With each step in time, we get more information. So that's what filtrations are all about. So here is the definition. So say we have a probability space, our usual omega fp. And a filtration on this probability space is a sequence of increasing sigma algebras on omega. And the sequence of increasing sigma algebras gives us successively more information, finer information. Okay.
So what do you mean by increasing?
Increasing more elements, yes, possibly smaller elements. So let's get some notation for this, because that's the definition in words. Here's the definition in math, that for all t greater than or equal to 0, and we can think of t as time, that f sub t, the filtration at time t is a sigma algebra, f sub t, this is a sigma algebra on omega, and the successively more information part is the following, that s less than or equal to t implies that f sub s is contained as sets of sets. We have this inclusion. F sub s is contained in f sub t, and this f sub s is coarser, and f sub t is finer. So this is the definition of a filtration. Questions about it? We're going to do an example soon. For every filtration, there's also a sequence of corresponding partitions that divide the space into successively finer and finer pieces. So this is possibly infinite in a sequence. The example I'll do is finite, but you can imagine extending this to infinite.
And this will include all the sigma algebras?
Does it include all of the sigma algebras? Maybe, maybe not. Was there another question over here?
So it's a single parameter family of sigma algebras. Do they form a semi-group?
So it's a one parameter family of sigma algebras. Well, depends on what you mean by a semigroup. These are sets of sets, so it's not obvious what the semigroup operation is. And that's beyond the scope of this course. So we could write these partitions also as capital pi sub t. And this is, usually we're thinking of t being in the positive reals. Also, a possibility is that t is a discrete parameter, so t might be in the natural numbers. Or it might even be finite, which is what our example is going to look like. So let's do our favorite old example, two fair coins, and we'll find a sequence of increasing the sigma algebras on it, a filtration. Okay, so omega is h comma t squared. It's got 4 points in it. Let's say that our first sigma algebra, F0, is the coarsest partition. So we want to go from coarser to finer. The coarsest partition we know is, or the coarsest sigma algebra is this one with the empty set and the whole space. And so this is the coarsest. It has no information in it. We cannot tell any of these outcomes apart according to this sigma algebra. Then we want something a little finer. So how about this? Let's have F1 be the information from the first coin. So the sigma algebra associated to this will be the following. There's HHHT in it. There's THTT, and then all of omega. And this is the information from observing the first coin only. So this is partial information, but more information than F0. And then our F2 is going to be from observing both the first coin and the second coin. And so what are the elements of F2?
Empty set plus 4 outcomes and
Okay, empty set plus a bunch of stuff, and there's a simple way of writing this. 2 to the omega, thank you. So, so we can see that indeed F0, it only has 2 things in it, and those 2 things are in both F1 and F2. So in particular, F0 is a subset of F1 as a set of sets. And then F1 has some of the things in 2 to the omega, but not all of them. But it is a subset of 2 to the omega. So we have this inclusion. This is an increasing sequence of sigma algebras. It's a filtration. It's a finite filtration. There are only, say, 2 time steps, which is natural because we have 2 coins. We observe one, and then we observe the second one.
And if you remove F1, it's still called filtration, right?
If we remove F1, yes, it's still a filtration, just a little simpler. In fact, it's like this one is the simplest possible filtration. And our examples last time are basically this example. So, other questions? Okay, now how are filtrations related to random variables? Because in this example, we've got our 2 coins. We observe one of them. So there's a random variable lurking behind this information for the first coin. And then there's another random variable lurking behind the second coin. And somehow this filtration is associated to those random variables. So in general, there's a way of doing this, of getting a filtration from a sequence of random variables. Okay, so this is another definition. filtration generated by a sequence of random variables. And let's call our random variables x sub n. I'm thinking of n in some index set, possibly the natural numbers, possibly finite. The filtration generated by a collection of random variables is defined this way. First of all, we're going to call it f sub n. And it's defined in words first, and we could create notation for this. This is the coarsest sigma algebra on omega. So x sub n, each of the x sub n's is a map. Oh, we have multiple i's floating around. Let's maybe go like this. N, the naturals. The coarsest sigma algebra on omega such that the vector of random variables x1 sometimes starts from x0, but let's do x1 here. x2 up through xn. This vector of random variables is measurable. And these are joint random variables. And so there's a notion of jointly measurable, which is exactly analogous to the definition of measurable that we had before, just higher dimensional. So we take these random variables, we look at what sigma algebras they are measurable with respect to, and then we take the coarsest such one of those. So the coarsest is the smallest in this inclusion sense, but the coarsest might have the largest blocks in it, the largest pieces. So for instance, in our 2 coins example, what are x0, x1, x2? So x0 is not so interesting. x1 is where things get interesting. So what should x1 be? The random variable that generates f1. What should x1 be? Sorry, again? The outcome of the first coin. So how will we express this? Let's have it be 1 if the first coin is heads, and 0 if tails. So this is an indicator random variable telling us what the first coin is. And here's one way that I like to write this. When working with coin flips, it's useful to use this kind of notation. So H star, H means the first coin is heads, star means the second coin is anything. So H star is a set. In fact, it's this set. And we're taking the indicator of this set. And this indicator generates this sigma algebra. There is another indicator that generates the sigma algebra. The indicator of the second set here, which is also 1 minus x1. It's flipping the 1 and 0. So there could be several different random variables that generate the same sigma algebra. This is one such that generates, this generates f1, and then we need a second random variable, x2, so that we're going to define this so that x1 and x2 together generate f2. And what should x2 be? So again, we have choices. X2 could be, there are multiple answers to this. Can you think of one?
Enumerate all four cases for 2.
Okay, enumerate all 4 cases. That's complicated. Let's get a simpler one. The number of heads. I'm not sure. So again, this is complicated. There's a simpler one. I think that would work. I think that it wouldn't distinguish HT from TH, right? Okay, so that wouldn't work.
You just do like star H.
Star H. But we need slightly more than just star H. We need the indicator of star H. So this is the indicator. This tells us what the second coin is. So this is 1 if second coin is H, and it's 0 if not, if the second is tails. Okay, so this is efficient. This is just the information about the second coin. It doesn't say anything about the first coin, but that's okay, because together, because this filtration is about all of these random variables together. So when we put x1 and x2 together, then they generate f2. So we can say that our filtration f0, f1, f2 is generated by these 2 random variables, x1 and x2. You can check that f1 and f2 are the coarsest sigma algebras generated by x1 and by x1, x2. This is an exercise you can do. So just to write this down, Fi are the coarsest sigma algebras generated or such that x1 and x1, x2 are measurable with respect to them. Okay? Questions? Okay, so we have random variables. They can generate a filtration. And we know that sigma algebras correspond to partitions. So if we have a sequence of random variables, we know how to define the filtration. Now how do we find a partition, a sequence of partitions that correspond to these? That's the next thing. So one way of defining these partitions, and we can write down what these partitions are in our example. Right? Pi 0 should be what? Just omega. It's the partition that lumps everything together. And then pi 1 should be the partition that separates the first coin being heads from the first coin being tails. And this is a finer partition than pi 0. And then pi 2 is another partition that corresponds to this power set, F2. And which partition is it? Singletons. It's this collection of all singletons. And these, let's see, it's not particularly a nice way to write this. So there's HH, HT, TH, and TT. 4 things in this partition. They're all separated from each other. So now how can we do this in general? And here is how we do this. So pi n is going to be a collection of sets written the following way. So F sub, and now there's this vector as its multi-index. F sub I 0 up through in. And then we take the collection of all such sets. So I 0 up through in they live in the index set. And let me tell you how we define this set Fi0 up through in. So Fi0 through in is defined to be the intersection of some sets of xk inverse of ik and the intersection over k equals 0 up to n. So let's remind ourselves xn is a map from omega to I. So we take, so there's another way of writing this in a moment. Xk is a map from omega to I. We take a particular ik that lives in the index set, and then we pull it back to this set, which is the inverse of ik under the map xk. And then we take all of these such sets and we intersect them. For a particular multi-index, ik, we get this set Fi0 through in. And then we take all the possible different multi-indices, and we get all possible intersections of these inverse images under the random variable. So here's another way of writing this, which might clarify. It is the set of all omegas, all outcomes in the sample space, such that for all k from 0 to n, xk of omega is equal to ik. This, by the way, you might have seen something like this in a different context. These are called cylinder sets, which we might sometimes refer to them that way. Okay, so this is how we can get partitions from random variables. So we can take a sequence of random variables and we can generate a sequence of sigma algebras, a filtration. We can also generate a sequence of partitions. And there's a correspondence between them. So we're coming up on the last couple of background topics in probability. And then the next class period will be on some background topics in linear algebra. And by the end of this week, I hope to define a stochastic matrix. Maybe we'll do our first real Markov chain example. Any questions about this before we move on?
Those I0 to In kind of like multidimensional index.
It's a multi-index. I0 through In is a multi-index. You can also think of them as coordinates. Okay, so the second to last probability topic is the moment generating function. So the moment generating function MGF for short, of a random variable x is defined this way. First of all, its name is capital M sub x, and it's a function of a parameter t, and it's defined to be the expectation of e to the tx. So in concrete terms, for random variables that we are typically dealing with, random variables that have discrete values, this expectation is the sum over j in capital I of e to the tj times the probability that x equals j. So who in the class has seen moment generating functions before? Excellent. Okay. Who has seen Laplace transforms before? Who knows that they're the same thing? Excellent. So knowledge that you have about these things from other contexts, I hope will be helpful. This is like a discrete Laplace transform. There's also a continuous version if the random variable takes continuous values. So here is why it's called a moment generating function, because it actually generates the moments. And I need to tell you what the moments are and how they get generated. And then an important property of the moment generating function is that it's multiplicative for independent random variables. And this fact about MGFs is actually connected to your question from last time, Wednesday. What's your name again?
Joseph.
Joseph? So I'll answer that question in a moment. Okay, so here's a fact. The moment generating function is multiplicative for x and y independent. So if we have independent random variables, then the moment generating function of x plus y, which is a function of t, is equal to the moment generating function of x times the moment generating function of y. And this is true for all t. And then as as an aside, to answer Joseph's question from last time, so by the way, this is expectation of e to the t x plus y. We can write this side, expectation of e to the tx, expectation e to the ty. So if this equality holds for all t, that's the important thing, not just for t equals 1, but for all t, then we have a good chance of x and y being independent. In fact, there's actually a vector version of the moment generating function. We need to look at expectation of e to the t1, t2, x, y, so a dot product here, and that should be equal to the right thing. And if it is for all t1 and t2, then they're independent. So that's an aside about independence. And then, what is the moment, the kth moment of a random variable x? So the first moment is the mean, the expected value. More generally, the kth moment is the expectation of x to the k. And as a definition, remember we talked about the expectation of a function of a random variable. X to the k is a function of x. And so we can define this expectation as the sum over j and I, j to the k times the probability that x equals j. So this is the definition of the kth moment. Now, how does the moment generating function generate the moments? Well, it's the following theorem. So, if we take our moment generating function, m sub x of t, and then we take derivatives of it, so the kth order derivative with respect to the argument t, and then, we're not quite done, we have to evaluate the result at t equals 0, and that will be the kth moment. So one can prove this through Taylor series. And there's the second moment is closely related to the variance, which tells us something about the width of a probability distribution. And we can get the variance from the first two moments. There are several ways of calculating variance. We write it as var of x, or sigma squared, where sigma is the standard deviation. And either of these notations we define as the expected value of x minus e of x quantity squared. Or, equivalently, sigma squared can be defined as the expectation of x squared, that's our second moment, minus the square of the expectation. And these two things are not usually equal to each other. They're usually different. This one is always at least as big as this one, so this quantity is always non-negative. And these are two different ways of computing it. Depending on the setting, you might use one or the other. But the variance tells us how much a random variable deviates from its mean, kind of typically. All right, so the last topic of our probability background will be convexity and Jensen's inequality. So, what is convexity? It's a property of a function, f. I'm thinking of this as a real valued function on R. So f is convex if and only if for all alpha between 0 and 1, and for all x and y and r, we have that f of alpha x plus 1 minus alpha y is less than or equal to alpha times f of x plus 1 minus alpha times f of y. And the proof I'll leave as an exercise. Basically, if you draw a picture, you'll see how it works. And then Jensen's inequality, it tells us how convexity plays with expectation. So Jensen's inequality says that if we have some f like this that is convex, then if we look at f of the expected value of x, so expected value of x is a number, f is a function, a map from the real numbers to the real numbers. So we can take f of v of x, and the result that we get is less than or equal to the expected value of f of x. Now here, x is a random variable. F of x is a function of random variable that is, again, a random variable. We can take its expectation, we get a real number, and we have this inequality. So some particular kinds of functions we run into over and over, and we can use Jensen to bound or approximate things.